We were looking at these geometric series and telescoping series, and those two particular types of series, we can actually find what they converge to. So if we can do more than just talk about a geometric series converging. We can actually say the specific number that it converges to. But for the most part, when we're dealing with series, infinite series, we're not going to be able to do that. We're not going to be able to say it converges to a particular value. We will just have to be content to say it converges or it diverges. And that's it. So a lot of the tests that we're going to learn is going to deal with that, just determining if something converges or not. Now, the first test that we're going to look at is called the Nth Term Test. And the Nth Term Test does not tell us if a series converges. It will tell us definitely if a series diverges. So when we look at this test, realize we can't use this test to determine if something converges. What we use this test for is to rule out convergence immediately and say, well, it definitely diverges. But so here's the thing. Here's what the test says. Let's suppose that we've got a series. N goes from 1 to infinity of a sub n. And you notice that you've got this little sequence in here. If we do this, if we say, well, let n go to infinity a sub n, if that does not equal 0, okay, so this must equal 0 for this to converge. So if this converges, then this is true, okay? That has to be, that's a necessary condition. It's not sufficient though. Okay? It's definitely not sufficient. So let me show you what I'm talking about. Let's suppose that we have a series, n goes from 1 to infinity, and we have something like 2n plus 1 over 3n plus 1. Okay? And we're wanting to know, does that series right there converge? Well, the first thing we do is this nth term test, because we might be able to say, no, it doesn't, and just go about our business. Because if we find that there's a possibility it converges, then we have some work to do. So here's a really quick screening that we can do. We can say, well, let's just look at the inside here. 2n plus 1 over 3n plus 1. Now, that limit is 2/3, which is not 0. Okay? So we can say definitely that this series diverges. So it diverges, definitely. And we don't have to go any further with it. Because what we've done is we've ruled out convergence, and there's no point in even continuing. If we're just trying to determine if a series converges, this tells us it does not. It's a screening, right? Now, that's a necessary condition that that limit be 0, but it's not sufficient. Because I'll tell you this. If you look at these two series, let's suppose we've got n equals 1 to infinity of 1 over n. And let's look at another one. N goes from 1 to infinity, 1 over n squared. Now you notice both of these, if you look at the limit of the inside, so if you look at this limit, n goes to infinity of 1 over n, yeah, that's 0. That's 0. However, this right here does not converge. On this one over here, though, the limit is n goes to infinity of 1 over n squared. It equals 0, but this one does converge. So on the one hand, so the nth term test gave us the go-ahead. It said, okay, the limit of the inside is 0, so maybe you want to investigate convergence. So we couldn't rule out that it converges. So we go on and do some more work, and what we're going to find out later is how to tell that that one diverges and that one converges. In fact, we're going to do that when we talk about the integral test. But this is the nth term test. And this is always the first thing you look at when you're going to investigate a series to determine if it converges or not. Now, you might, to see why this works, let's just think about a series. let's suppose that we've got a series, and let's suppose that this series does converge. Okay? So let's suppose it does converge. Now, so this right here is equal to some number. Well, if that's true, then here's what you have. You have the limit, it equals this number right here, right? So I mean, that's what we mean by convergence. So we know that this series converges. Now, so this is the nth partial sum. Now let's just take a step back then and say, well, what about the limit as n goes to infinity of the partial sum right before n, the n minus 1 partial sum? Well, that's going to be L as well, right? I mean, it doesn't really matter. We're just kind of playing a game here, saying, well, if the nth partial sum converges, well, the sum before it converges, right? If you let n go to infinity, right? So it doesn't matter. This is S sub n, this is S sub n minus 1. They're both going to converge to this, right? Do y'all see that? There's no question about that. It's just, we're just kind of playing a game of notation here. So now realize that S sub n minus 1, let's do this. Let me go back a little bit. S sub n is equal to S sub n minus 1 plus A sub n, right? That's true, right? In other words, the way we get the nth partial sum is with this. We take the partial sum previous and then add the next term, right? Y'all see that? Any questions about that? Okay? Now, so we're on solid ground here. Now, if I take the limit as n goes to infinity of S sub n, that's exactly the same as taking the limit as n goes to infinity of S sub n minus 1 plus A sub n, right? Just a little substitution. Isn't that correct? Now, remember what we said. We said that the limit, this thing converges to L, right? We said that. So here's where we stand now. This is equal to the limit as n goes to infinity of S sub n minus 1 plus the limit as n goes to infinity of A sub n. I just I broke this apart. Now this definitely, this is, whoops, this is L right here, right? This first sum. Well, that's what the series converges to. Therefore, this must be 0 right here, right? That would have to be, because this is an extra term. If this is anything but 0, then the series doesn't converge to L. It converges to L plus something else. Okay? So it's necessary that this nth term has to go to 0. That's a necessary condition, and this illustrates it. Okay? Any questions?